Okay. So today, this is the last of the particulate removal lectures. We'll move next week to looking at specific gases and how we can remove those gases. So actually, this is a good lecture in terms of transitioning, because as you'll see with wet scrubbers, we can actually remove some gases through wet scrubbers in addition to particulates, but the real focus of the design of these systems is on particulates. So with wet scrubbers, we're looking at dividing the flow. So we're looking at dividing this gas flow by sending it through many droplets of water. So you can kind of think about what a wet scrubber as you can think of a rainstorm. Springtime, there's lots of pollen in the air, and what happens when it rains? Well, the pollen particles collide with the raindrops, and those pollen particles essentially drop out of the atmosphere, so that you'll typically see much lower concentrations of particles right after a rainstorm. Essentially, we do the same thing, except in an engineered process. So for instance, this is an example, and what we have is we have a gas. So we have a gas stream that enters a contactor. So it's in that contactor that the description of that rainstorm. So those particles in the dirty gas contact with the liquid particles. Now, the way that this is set up is it separates out the contactor and the separator. These actually can be combined into one unit. But what you then have is a gas separator. So in this case, it's shown as a cyclone. So what you're trying to do here is separate the liquid particles from the gas particles, or those liquid droplets really, from the gas itself. So the particles, the particulate material that was in the gas is transferred to the liquid. And what we then have is clean gas that we can emit from a stack, and we have a liquid that contains those particles. So what we've done is essentially to transfer those particulates from the gas phase to a liquid phase. We then need some sort of a solid liquid separator. It's often a gravity settler. So we then have the solids that we can collect, and ideally we have clean liquid that we can then recycle and reuse in the process. Typically, we're looking at removing particles that are between about 0.1 microns up to 20 microns in size. And the major goal of the contactor is, what we want is adequate dispersion of the liquid, typically water, okay? And we want good contact with the particulates in the gas. So shown here, we have a boiler, we have the gas stream. So it's a combustion process where typically we'll have particulates here. We will be, okay, so we have some level of particulates. In this case, what this is actually showing here is that we get both gas removal. So what we're actually removing here is SO2 and the particulates. They end up in the liquid stream, and then we have clean gas. Okay, so that's our goal. Okay, the goal is to move from a liquid phase, sorry, from particles in the gas phase to particles in the liquid phase. We've talked about, with filtration, we talked about inertial impact, interception, and diffusion. Diffusion being for those very small particles, interception and impaction for the larger particles. Here it's not a fiber that you're trying to impact or contact the particle, but it's the droplet. So it's basically, you can envision the same sort of video, except instead of a fabric, it's the gas is moving through this kind of maze of liquid droplets. Now, the efficiencies on these units are extremely variable, and they are dependent on a number of terms. One is the gas velocity, and you can see it here. Okay, so we have gas velocity here, and as the velocity of the gas increases, so does the efficiency. In order to get good removal, we need to have sufficient contact between the gas and the liquid particles. This ratio of the liquid to gas flow rates is referred to as R, and as you can, we have in this equation here, and as R increases, so does the efficiency. Now, there's an optimal ratio between the diameter of the particle and the diameter of the liquid droplet. And you can see it in this figure here. We have plotted the target efficiency versus the diameter of the water droplet. And you can see, especially for these really small particle sizes, the diameter of the droplet has a very significant impact on efficiencies. And you can see where efficiencies are low. When we're looking at a 10 micron over that same range of water droplet particle size, the efficiency of removal is close to 100%, and it doesn't vary significantly with water droplet size. So this, we have a ratio here, but the impact is on efficiency is actually even more significant than what it might appear from the ratio of the diameter of the particle squared divided by the diameter of the droplet. And as you can see from here, as we increase the diameter of the particle, the efficiency increases. As we increase the size of the water droplet, the efficiency is going to decrease. The temperature plays an important role, mainly on viscosity. So as temperature increases, viscosity increases, and then the efficiency decreases. The two terms that we use here, okay, this term phi is described as the inertial impact factor. because when we're looking at removal, it's really inertial impact that plays the most significant role in removal. Now, looking at the different types of scrubbing units, there's two different types that we have here. And so what you see on your right is a countercurrent flow. So we have gas coming in, moving past the recirculated water. And then we have liquid flowing in the opposite direction. And if I could get this to work today, I switched to tablet mode, see if it would work better. Not necessarily. And then here we have a cross flow unit. So now you can see the air flows in this direction. The water flow is in this direction. So your gas flow is perpendicular to your water flow. Both cases, what you're trying to do is achieve good contact between the gas and the liquid phase. You need a gas flow rate that is sufficient to keep the water droplets suspended. If the water droplets just fall, the faster they fall, the less contact you have. So if the gas actually keeps those water droplets in suspension, then you've got more time for mass transfer of the particles or the gases, as I showed you before, to be transferred across the air-water interface and then into the water droplet. Okay, so this really is a phase transfer, because you're looking at, if I draw it here, here's my water droplet. I'm going to switch to the pen. And I have my particles out here. And what I'm trying to do, or in the case if I have SO2 gas, and I'm looking at transferring those particles, I have to have a collision, and I want to transfer it into that droplet. So the longer I can suspend that particle, the more opportunity there is for mass transfer. You also typically have to replace some of the water. You see this, we have recirculated water here. So you've got some sort of a settling basin, and then that water is recycled here. If your gas is hot, then you're going to have evaporative losses of water, so you'll need some makeup water to replace that water that's evaporated. Typically, the nozzles have sort of a cone shape, and they seem to be the most effective. And in terms of efficiencies, for particles around 8 microns in size, you can achieve up to about 90% efficiency. Larger particles, 25 microns, you can actually achieve 99% efficiency. One of the major advantages of this is the low pressure drop. Smaller the pressure drop, the smaller the pump that you need. And typically relatively low power inputs. These are used in, for instance, in paper towel manufacturing to control paper dust. It's controlled in fiberglass production to control latex aerosols. It's also spray cyclone chambers. So this is essentially a cyclone separator combined with a scrubber. So you can see the same sort of tangential entry and that circular pattern. So the gas is moving in a circular pattern, just as we've talked about with cyclone separators. And water is sprayed out. So basically what happens is the spraying of the water out, the water sprayed outward to the wall, the particles are sprayed outward to the wall. And this actually promotes very good droplet separation, good mass transfer, so good efficiency. And it's relatively easy to manufacture because it's basically a cyclone separator with banks of nozzles in a ring inside a conventional cyclone. Typical efficiencies are greater than 90%, 99% for fairly large particles. Just giving you some typical characteristics of these in terms of their inlet velocity, quite high. Typically, you're looking at liquid circulations, about 2 to 10 gallons of water per 1,000 cubic feet of air treated. And these have a higher pressure drop than the spray chamber. So you typically get better efficiencies, but you're producing more contaminated water. So that's one of the major disadvantages with these systems, is you're transferring a gas problem essentially to an aqueous or liquid problem. Another type of unit is referred to as a sieve plate scrubber. Again, what you're trying to do is create this transfer. So basically, these are sieve plates. You can see there's multiple plates in these. You've got air coming in through the bottom, so your air is moving upward, and your liquid, so it's again a cross flow, counter current. So it's a counter current flow. Sorry, it's counter current. So you've got a counter current flow, and what typically will happen is you get a kind of a froth develop on top of the perforated sieve, and that actually helps to ensure good contact between these water droplets and the gas itself. There's other similar units like this, a column, but instead it's with packed materials. So basically, you can think of kind of packed balls, like a wiffle ball, but smaller than that. So basically, some sort of, it's just a packed material. Typically, these have a lot of openings in them. They could be more kind of like openings like this, but basically what you want is a lot of surface area, and then you've got, again, the gas coming in, you've got water coming, so water's down, gas is moving up. And again, you're trying to ensure good contact. Okay, again, these have a relatively high, and that's one of the disadvantages of these. You can see as we kind of moved through these different processes from this from the simple chamber to a cyclone to the sieve plate, the pressure drop is actually increasing. So you're going to use more energy to separate these particles. And then we have Venturi scrubbers, these typically are operated with a cyclone separator. The difference is you have a Venturi here, and you're actually adding the liquid and the gas at the Venturi. The water and gas flow through that Venturi, and the negative pressure actually pulls the gas in, or the decrease in pressure. So typically here, efficiency is greater than about 98%. For relatively small particles, you want to operate these with relatively small particles, because you've got to ensure that you don't have clogging at that throat. You're relying on the Venturi rather than a pump. These are simple, they're easy to install and maintain. The power input is about 3 to 12 horsepower per cubic feet per minute. So it's a relatively high power input and a large pressure drop. So this is the big disadvantage of these units. And this is just another schematic of a Venturi scrubber with a cyclone separator. One of the major advantages of a wet scrubber is that if you're treating a flammable or an explosive dust, this minimizes the risk of explosions or fires. So it's a significant advantage of this process versus a dry removal process. Unlike the other processes that we've talked about, as I mentioned here, you can achieve gas absorption into the liquid and dust collection in one unit. So for instance, as I showed you with the boiler flue gas treatment, that can be used for SO2 removal. So you're looking at a gas removal, and you're also looking at particulate removal. It can handle gases that include a mist, so moist gases. Remember, if we mentioned that on a fabric filter, if you have condensation on the inside of the filter, then you have greater potential for corrosion, and that results in a deterioration of that fabric. If you have very hot gases, the water cools that. So in terms of subsequent treatment, you've already cooled the gas, and you don't need an additional process in order to cool that gas. You've got variable collection efficiency. You can try and adjust that with trying to change your droplet size, your liquid droplet size, to optimize that. And lastly, you can neutralize corrosive gases. So for instance, as mentioned, as shown in that image of the flue gas treatment, they'll be using limestone. So they're using limestone to neutralize the SO2, or the sulfuric acid, that forms when SO2 is in contact with water. The disadvantage is if you don't neutralize a corrosive gas, then you have a high potential for corrosion. So you have to address the potential impact of corrosion. The other major problem is that you're simply transferring your contaminants from the gas stream to a water. So you start with contaminated gas, you end up with contaminated water, and then you need to treat that contaminated water. Depending on how large this unit is, where it is operated, freezing can be a significant issue. And another issue is that because your contaminants are now in water, they're moist, so it may make it more difficult to recycle that material. So if you think of that drop box, if we're looking at aluminum chips or material from a foundry, we then have to take that material, we want to recycle that. But in the case of a wet scrubber, that material is mixed with water, it's wet, we have to dry that before we can recycle it. So depending on whether you want to recycle a material, wet scrubbers may or may not be the optimal process. And then lastly, since your contaminants end up in water, then you end up with a aqueous waste or sludge that will typically have a high moisture content. Therefore, you've got a high volume, and that either treatment or treatment and disposal can be expensive because of that. So we're going to look at one problem. I'm going to switch mode. I did not want to do what I just did. Okay. I'm switching back to the normal mode that I use because I can add slides easier here. So we'll look at one problem where we'll calculate the efficiency of a wet scrubber. Okay. So what we're looking at is we're looking at a scrubber that we're removing 10 micron sized particles. And these particles have a density of 700 kilograms per cubic meter. We're going to use that Venturi scrubber that I showed you before. And the Venturi has a throat area of 1 meter squared. We have a gas flow rate of 94 meters cubed per second. We have a gas temperature of 150 degrees C of 423 Kelvin, a liquid flow rate of 0.13, a correlation coefficient of 200 meters cubed of gas per meters cubed of liquid, and a droplet diameter of 100 microns. So let's add a new slide in here that we can work with and switch colors. Okay, so let's just again reiterate what we have. So we have a diameter of the particle of 10 microns. We have a density of the particle of 700 kilograms per meter cubed. We have a throat area of 1 meter squared. We have a gas flow rate of 94.4 meters cubed per second. A gas temperature of 150 degrees C or 423 Kelvin. A liquid flow rate of 0.13 meters cubed per second. A correlation coefficient which is K in the equation that I gave you before. It's actually kappa in the equation, and that is 200. And a droplet diameter of 100 microns. Okay. The first thing that we need to do is we'll determine what is referred to as the Cunningham correction factor. And this is introduced because these very small particles don't obey Stokes' law. So for settling, they tend to slip between the gas molecules, and you can think of slip, talked about it, probably talked about it in 321, fluids. So slip, if you have a flow across and you've got a boundary layer, so if you think of a pipe, we assume that the velocity of the water at that boundary is 0. So at the outer wall is 0. When a liquid doesn't, when it slips, okay, basically that velocity is not 0. Okay, so you can think of the velocity of the gas along a water droplet. The velocity is not 0. So it slips between the glass, or the water molecules slip between the glass molecules. The coefficient of drag is reduced, and the particles fall faster than what's predicted, okay, because the velocity is not 0. And this is especially true when the diameter of the particles is less than 1 micron. So you're going to see more slip the smaller the particles. And this is equal to 1 plus 6.21 times 10 to the minus 4 times the temperature in Kelvin divided by the diameter of the particle in microns. So this is equal to 1 plus 6.21 times 10 to the minus 4. So make sure if you're using this, your temperature is in Kelvin, your diameter is in microns, and this is equal to 1.026. So it's about a 2.6 change in the velocity of these particles. The velocity of the gas is equal to the flow rate of the gas divided by the area, that throat area. Okay, that's the velocity that is most important. So we have 94.4 meters cubed per second, 1.0 meter squared. So the velocity of the gas through that throat is 94.4 meters per second. The viscosity of the gas at 150 degrees C is 25.2 times 10 to the minus 6 Pascal second. So this inertial impact factor, we need to multiply by the Cunningham correction factor times the density of the particle times the velocity of the gas times the diameter of the particle squared divided by 18 times the diameter of the droplet times mu. So notice that looks a bit like Stokes' law. So if we substitute, this is equal to 1.026 times 700 kilograms per cubic meter times 94.4 meters per second times the diameter of the particle. We need to convert that to meters, and that is squared, and we'll divide by 18 times 10 to the minus, or 10 times 10 to the minus 6 meters. So that's the diameter of the droplet. And the viscosity. And that is equal to 146. So that's the inertial impact factor. So that's let's add another slide in here so we've got some space to finish this. The efficiency then is equal to 1 minus e to the minus kappa, so the correlation coefficient, times r times the square root of the inertial impact. Obviously, this is an empirical equation, and this is equal to 1 minus exponent of minus 200 times r is 0.13 divided by 94.4, just times the square root of 146, and that is equal to 0.964 or 96.4%. So we would predict 96.4% removal of these 10 micron sized particles if we had a droplet diameter of 100 microns and with the system that we've described. So having looked at a number of different processes that we could use for treating gases, what I want to do in just the last few minutes is look at how we might choose a collection device. Okay, so how would we collect these particles? What are the factors that we would take into consideration? So with sticky particles, particles that are hygroscopic, these are much more difficult to remove. It may be necessary to use some sort of a throwaway device or to use a wet scrubber so that you're contacting those particles with a liquid and then removing them from the liquid. Throwaway device could be a HEPA filter, simple as what you have in a furnace. Recommended that on a quarterly basis you remove that HEPA filter, replace it with a new one. Could be an air filter on a car. All of these are disposable devices that are used to remove particles. And they work with sticky particles, they work with dry particles. Problem with a liquid is then you have that liquid that you need to then treat. And that's true with a wet scrubber. ESPs, the electrostatic precipitators that we talked about, can also be operated in a wet mode, so with a liquid. So you're again contacting those particles with a liquid. Again, you've got a liquid that you have to process and treat. These sticky particles may be able to be removed with for instance, a cyclone separator, but where the surfaces are coated with a non-stick material like Teflon. Now, particles that tend to agglomerate, so they tend to attach to one another, so the particles actually grow in size. That typically makes them easier to collect. You want them to be able to contact one another and agglomerate, but you don't want that agglomeration to occur on the wall. Okay, now then you've got that sticky particle problem, and you have the problem of then trying to remove that particle from the wall. Depending on the electrostatic charge of the particle, ESPs may be feasible or not. So it's very important to know and to understand what the electrostatic charge is of these particles and how would they behave in an ESP. Large non-sticky particles, cyclone separators typically are the preferential option. They're easy to operate. They don't have many mechanical parts, so they're slow to maintenance. They're inexpensive. So you'll often see cyclone separators used for these larger particles. Particles that are less than 5 microns, typically you're going to look at ESPs, baghouse filters, wet scrubbers. Again, it depends on, are these particles hygroscopic? Are they charged? What's the electric resistivity of these particles? So can they be removed in an electrostatic precipitator, or do they need to be modified in some way? If you have large gas flows, that typically means that you have a large water volume that needs to be, or flow rate that needs to be treated, and that makes scrubbers expensive. And it's not the scrubber really that's expensive, it's the water treatment and disposal that's expensive. And then finally, if you have corrosive gases, wet scrubbers may be useful if you can neutralize the corrosive gas. You need to be very careful with using, for instance, filtration with typical, less expensive materials because of corrosion of those fabrics, deterioration of the fabrics. You may need to use special materials. For instance, a ceramic. You can use ceramic filters. They tend to be much more robust, but they're more expensive, and they need to be very large because of the porosity of the ceramic material. So we will end there with particulate removal, and I'm happy to answer any questions that you may have. Any questions? No questions? Okay. Since we have no questions, I will end for today. Happy to answer any questions online. Otherwise, I will meet with you on Monday. For those of you celebrating Easter and Passover, happy Easter, happy Passover, and stay well, stay safe, and stay home. Take care and have a good weekend.